Welcome back, legends, to another Budfellas educational deep dive. In this episode, we're exploring how heat stress develops in cannabis plants. This content is purely educational and focuses on plant biology, physiology, and environmental response. We are not discussing how to grow, control temperatures, or fix problems. Instead, we're explaining what heat stress is, how it forms, and why plants respond the way they do. As always, this content follows UK law and YouTube guidelines. The aim is understanding plant behaviour, not instruction. Before we jump in, remember, this channel is for viewers over 18, and our content is purely educational. We're not here to promote or encourage illegal activity. In the UK, cannabis cultivation remains illegal without a licence. What we are doing is learning plant science and helping beginners avoid common mistakes. Quick update. We've just launched the Budfellas Telegram community, connecting growers and enthusiasts from around the world. It's legal-focused, all about networking, plant science, and shared experience. Links in the description. To understand heat stress, we first need to understand how cannabis experiences temperature. Plants do not feel heat the way humans do. Instead, temperature affects the speed of chemical reactions inside plant cells. These reactions are controlled by enzymes, and enzymes operate within specific temperature ranges. When temperatures rise beyond those ranges, efficiency drops. At normal temperatures, enzymes work smoothly. Photosynthesis, respiration, and energy transport stay balanced. As temperature increases, these reactions speed up, but only to a point. Beyond that point, enzymes begin to lose their shape, reducing their effectiveness. This is when stress begins to develop. One of the earliest effects of rising temperature is increased respiration. Respiration is the process by which plants convert stored sugars into usable energy. Under heat stress, respiration speeds up faster than photosynthesis. This creates an energy imbalance, where the plant burns energy faster than it can replace it. As this imbalance grows, the plant must make choices. Energy that would normally go toward growth or flower development is redirected toward survival. This shift is subtle at first, but becomes more pronounced as stress continues. Another major factor in heat stress is water movement. As temperatures rise, transpiration increases. Transpiration is the evaporation of water from leaf surfaces. This process cools the plant, much like sweating cools humans. However, excessive transpiration increases water demand and strains the plant's internal transport system. To reduce water loss, plants close their stomata tiny pores on the leaf surface. While this conserves water, it also limits carbon dioxide intake. Reduced carbon dioxide intake directly limits photosynthesis. This creates another layer of stress as energy production declines. Heat also affects cell membranes. Plant cell membranes are made of lipids that must remain flexible to function properly. High temperatures can make membranes too fluid, disrupting transport of nutrients and signals between cells. This disruption interferes with normal growth patterns. Hormonal signaling changes under heat stress as well. Plants rely on hormones to coordinate growth and development. Heat stress alters the balance of hormones such as auxins, abscisic acid, and ethylene. These hormonal shifts slow growth, reduce expansion, and prioritize protective responses. One of the most visible effects of heat stress is leaf posture changes. Leaves may angle upward, curl, or appear rigid. These movements reduce surface area exposed to heat and light. This response is protective, not a sign of failure. Heat stress also affects protein stability. Proteins are essential for nearly every function in the plant. High temperatures can cause proteins to unfold or malfunction. In response, plants produce heat shock proteins. These specialized proteins help stabilize other proteins and prevent damage. Producing them, however, requires energy. Another important aspect of heat stress is oxidative stress. High temperatures increase the production of reactive oxygen species inside plant cells. These molecules can damage cellular structures if not neutralized. Plants respond by activating antioxidant systems, but this again diverts energy away from growth. Timing plays a critical role in how heat stress develops. Short periods of elevated temperature may cause temporary responses with little lasting impact. Prolonged exposure, however, leads to cumulative stress. The longer the plant operates under imbalance, the more pronounced the effects become. Heat stress also interacts with other environmental factors. High light intensity combined with heat amplifies stress because the plant receives more energy than it can process safely. Low airflow can worsen heat stress by preventing heat dissipation from leaf surfaces. Another key point is that heat stress often develops gradually. Plants rarely collapse suddenly from heat alone. Instead, small inefficiencies accumulate over time. By the time visible symptoms appear, internal stress has often been present for days or weeks. Different parts of the plant respond differently to heat. Young tissue is often more sensitive because cells are actively dividing. Older tissue may tolerate higher temperatures, but still experiences reduced efficiency. This uneven response creates complex visual patterns. Genetics also influence heat tolerance. Some cannabis genetics evolved in warmer environments and possess greater heat resilience. Others evolved in cooler climates and show stress at lower temperatures. These differences explain why plants respond inconsistently to the same conditions. Heat stress also affects developmental timing. When stress is present, plants may accelerate certain processes while slowing others. This can alter how resources are allocated throughout the life cycle. These changes are adaptive responses, not malfunctions. It's important to understand that heat stress does not exist in isolation. It interacts with water availability, nutrient transport, oxygen levels, and overall metabolic demand. This interconnectedness makes heat stress complex and often misunderstood. From a biological perspective, heat stress is not damage itself, it is the plant's response to thermal imbalance. The plant is actively adjusting to survive. Many visible changes are protective strategies rather than signs of failure. In summary, heat stress develops when temperatures disrupt enzyme efficiency, increase respiration, alter water movement, affect cell membranes, change hormone balance, and increase oxidative pressure. These internal changes lead to the external responses we observe. When heat stress is understood as a biological process rather than a mistake, plant behavior becomes easier to interpret. Cannabis is not fragile, it is responsive. Thanks for tuning in, legends. If you enjoy these calm, science-based explanations of cannabis behavior, stay locked in. This is Budfellas Educational, evergreen, and always within the guidelines, signing out.